In order to create X-rays, what we have to do is we have to take electricity and we have to manipulate it into specific energy levels, so that we have the quantity and the quality of X-rays that we want. So we have two things that kind of govern electricity, and that's voltage. So this semester, what we're going to talk about in voltage is it being the power, kind of the motor behind the electrons. So electricity is electrons, it's just moving electrons. We do have electrostatics, which are stationary, static electricity. We'll talk about that, I think, in chapter 4 or 5, somewhere along there. But we also have moving electrons. That's what we refer to as electricity. So the motor behind the movement of the electrons is voltage. The electrons themselves and the number of electrons that we create or use is what we refer to as amperage, and we shorten that to amp. Now, I forgot to ask, yesterday was your first clinical day. Anybody see anything fun? What'd you see?
I saw a guy break his ankle and the whole thing was out.
It was broken, dislocated?
Yeah.
Yeah.
It was out of the skin, blood everywhere.
Oh, okay, it was compound fracture.
Yeah,
Okay. Oh yeah, that's fun stuff, day one.
He hammered a nail into his kneecap.
Another guy hammered a nail into his kneecap, so a nail gun?
That was pretty fun.
Yeah, yeah, you got all the good stuff. Anybody else?
I saw surgery.
Surgery, day one.
Mm-hmm.
Where, what?
Palestine.
Palestine? Okay, okay. You're probably not going to see that in Tyler until about mid-semester.
I think you were in surgery.
I was in surgery too.
And where are you?
Oh, sorry?
Which hospital?
Oh, UT Athens.
Okay, Athens, okay, yeah. So, the benefit of those smaller clinical sites is you get exposure to things, because it might get a little bit slower. You get exposure to things sometimes that you just don't see quite as quickly as what you see in Tyler. But where are you?
Greenville.
Greenville? Okay. Greenville's a much larger hospital. It's not quite as big as the ones here, but it is a fairly large hospital, really close to a metropolitan area. So that doesn't surprise me at all, either one of those. That's great stuff. Day one, did surgery make you queasy at all?
Mm-hmm.
Okay, so this has nothing to do with this, but if you go to surgery, all right, so if you're at one of these smaller hospitals and you go to surgery, or if you are at a larger hospital and you finally get your surgery rotation, there's a time that you might get a little queasy in surgery and you might start to feel a little faint, right? So if somebody makes eye contact with you and they say you need to sit down, they don't mean you need to go find a chair and make yourself comfortable. They mean you got to get to the floor and do it now. Okay, so your thing is, make sure there's no sterile field behind you, back straight up to the wall, slide down the wall and sit down. Because you got about 10 seconds before you're going to be on the floor anyway. So it's a difference between an open head wound or you just back up to the wall and slide down. Because what happens is that when you start feeling fat, and I used to work in surgery. Most of my career, that's where I worked, was in surgery. And we see it all the time. You look up, somebody's slightly sweaty, and it's cold in surgery. That's a big alarm. It's cold and you're sweating. That ain't right, right? And then you turn white and then you fall. Okay, so if somebody looks at you and say, you need to sit down, that's immediate. Immediately you need to sit down, okay? So just if you happen to go on Wednesday or Tuesday, Thursday, whatever, and somebody says, sit down, okay? So anyway, back to this. To create X-rays, we have to have amperage and voltage. Where we get our electricity in the hospital is just like how you get it at the house. It comes from a power plant. Unless there's a power outage, they do have generators, right, to back up the power. Might even have a battery backup for a specific amount of time. But the type of voltage and amperage that we use is totally different than what you use for your oven, hair dryer, whatever, charge your phone and all that. That's straight voltage and amperage. What we use is kilo voltage. And by the way, I don't write well and I don't draw any better. Okay, so my handwriting's awful, my drawing I'm more of a Picasso than a Rembrandt, okay? So we use kilovoltage. What does kilo mean?
Thousands?
Thousands, right. And we use milli amperage. What does milli mean?
Million?
1/1000th, right? So we use very high voltage and very low amperage in order to create X-rays. So how does your electric drill work off of kilovoltage? No, it's straight voltage, so it's like 120 volts. So our power that comes into the house or into the hospital might be as low as 120 volts, and it may be as high as 440 volts, okay? But it's not gonna be higher than that. It comes to the hospital in very high voltage, you know, tens or hundreds of thousands of volts, but it goes into this box on a telephone pole outside of the hospital, and we call that a transformer. It's a transformer, right? So it goes into a transformer. So the easiest type of power plant to draw is a nuclear power plant. So that's what I'm going to go with. Electricity comes from the nuclear power plant, and it may be 100,000 volts. Okay, so we're already at kilovoltage, but it's going to go into the transformer on the telephone pole, and it's going to lower it through a process that we're going to talk about here in a minute to lower it to something that you can use. The problem is we need it back up to this. So we have to have in our imaging system something that will take what was sent to us and convert it back to something similar to what was sent to us, okay? So we have to have a way to adjust the power of the X-ray beam, and we have to have a way to adjust the quantity. So the amperage is just a measure of the number of electrons that you're sending through a circuit. Voltage is kind of the power behind it, okay? So how this equates to X-rays is this is power of the X-ray beam, this is how much of the X-ray beam you're going to create. Quality of the X-ray beam, quantity of X-rays you create, okay? We're going to use all of that and all that terminology this semester. Quality, quantity, and all that. So it comes out of that, and it goes into the hospital, into the X-ray room, and what it gets to is a type of one of these things, all right? But it's a specific type of one of those, and it is just kind of a curved wire, and it doesn't look like that. It's all compressed together real tightly, and I'll show you some of this throughout the semester. And it's got an iron core that's going through it, and what we do is we take electricity and we run it through that thing. So electricity has to have a way to come in and have a way to go out. So this is going to have two connections, okay? So we tend to think of one as being a ground wire and one as being a hot wire. Okay, but in actuality, what's happening is the electricity is going in and out, in and out, in and out. That's what we refer to as I'm going to run through a lot of these this semester. Alternating, what does alternating mean? Yeah, this hand, I'm alternating between hands, right? It's alternating current, so it's going in and out and in and out. All right, so what this thing is a type of transformer, but it's a specific type of transformer. This transformer takes that high voltage and it drops it down to one of these. Okay, it doesn't drop, you can't adjust it from this, but from this one we can. Okay, so this is a specific type of transformer that we call an auto transformer. And a distinguishing characteristic of an auto transformer is that you can adjust it. All right, so who had the air conditioning on this morning? Okay, did you adjust it? Okay, it's auto transformer, essentially. All right, so what an auto transformer is what we refer to as a rheostat. And a rheostat is just an electromagnetic device, and I'll explain what that is, later in the semester. An electromagnetic device that takes a a quantity of electricity and adjusts it up or down so that you can do more or less work. Okay, so you turn your air conditioning control up, more electricity to the fan, you get a colder car. You turn it down or off and it gets warmer in the car, right? So that's what that thing is. It's an auto transformer. It's still a transformer just like that, only it only has one coil of wire. Inside of this one, there's two, okay? And I'll explain all that in a bit, and it's actually going the opposite direction. It's got a real squiggly wire and then a less squiggly wire. All right, we've already gone through two of these. So the first thing that it gets to, sort of, and I'll explain the sort of later on, is the auto transformer. So electricity goes to the auto transformer. What do we do with the auto transformer? We use it as a rheostat so that we can adjust our power, in this case, of the X-ray beam, and we can either turn it up or turn it down. What's the importance of that? Do you think you need the same power to penetrate a finger as what you need to penetrate abdomen? No, you don't. So we need to be able to adjust the voltage, and that's where we adjust the voltage. This is our voltage adjustment. But we don't use voltage in X-ray, we use kilovoltage. So it's adjusting the voltage in anticipation of it becoming kilovoltage. Now, it works off, that's even worse. Holy smokes, not one of these things. What's that?
There's one over there.
Is there? Okay, maybe one last chance. This one is complete garbage. No better than the other two, but maybe we can limp through this with these three. All right, so it works off of, and it has to have alternating current. So the current comes in and goes out, comes in and goes out. What that does is it creates a changing magnetic field. Okay, so it changes magnetic field. Anytime you have electricity that goes through a circuit, you create a magnetic field. So we use that magnetic field to adjust our voltage so that if we were to plug into the secondary side, we're going to call the side that we give the electricity to primary, and that's what that 1O means. And a secondary side is the side that we don't supply the electricity to. We're going to get electricity out of it. But if we plug into the exact same spot on the secondary side of the auto transformer, then our voltage that comes out of the secondary side of the auto transformer is identical to the voltage that goes into the primary side. In other words, if I put 100 volts in, I'm going to get 100 volts out, okay? But if I take and I spread these out, and I'm going to teach you exactly how to calculate how much of a voltage change you're going to get on the secondary side of the
auto transformer,
based on how many of these turns you incorporate. So if you spread those things out, then your voltage is going to go up. Now maybe you have 120 volts. Okay? So logically, if I spread them out and my voltage goes up, if I squeeze them together, what's going to happen?
they go down.
They go down, right. So what you're doing is you're supplying alternating current to create a changing magnetic field so that we can change our voltage. If we spread them out, increase the voltage on the secondary side of the auto transformer over what we had on the primary side. Okay, that's how these things work. You got 100,000 volts coming in. It goes to a specific type of transformer. It's not an auto transformer. It's not a rheostat. It's just a transformer, and it decreases the voltage to these. Now it gives us this, and we have to adjust it again. Okay, but still, in the end, what do we have? Voltage. What do we need? Kilovoltage, right. So it's going to come out of that, okay? And let's, for sake of argument, we're going to say that it didn't give us 120 volts. We're going to just say it gave us 50 to make it more dramatic. We increased to 120 volts. Now it's going to go into a different type of transformer that's identical to this, only flipped around backwards, okay? So we got 120 volts. What did we feed this? Kilovolts, exactly. We fed it kilovolts and it fed us voltage, right? Now we're going to feed ours voltage to make kilovoltage. So what we're going to do is we're going to take this and we're going to flip it around. You see, I don't know if you can see this very well, but I got a lot of squiggles on this one, not very many squiggles on that one. If I flip it around, how many squiggles am I going to have over here? Just a few, right. Okay, and y'all are picking up on this very quickly, and I appreciate it. Generally, when I'm asking questions, I'm asking for generalities, right? I mean, if I point to something specific, I'm looking for something specific, but if I say in a word, how many squiggles am I gonna have? A few is it, not many. In comparison, in a word, I'm gonna have more, yeah, I'm gonna have more. So now what I can do is I can feed this type of current, and that is referred to as alternating current. So I'm going to feed alternating current into this, so the current's going to go in and out, and that's going to create a changing magnetic field. Okay? Now if I move this secondary coil, this is a primary coil, and again this is a secondary coil. If I move the secondary coil close enough that the magnetic field interacts with this coil of wire, then I create alternating current in that coil of wire, okay? So what I'm doing is I'm taking alternating current to create a changing magnetic field, which in turn creates an alternating current, okay? Again, this is like chapter 6 information. Don't lock up on it. It's fine. We're gonna build to this, okay? So now what I've got is what happened to my voltage. If my voltage went down here, I've got fewer turns on the primary side than what I had on the secondary side, and my voltage went up. Then I've got fewer turns on the primary side than I have on the secondary side. My voltage is gonna go down. It's still gonna go up. Fewer, more, up, fewer, more, up. Okay, so now what I've got is if I fed that 120 kVp, and again, I'm going to teach you exactly how to calculate this and how much of a change you're going to have. If my turns ratio is such that we have, that's getting too deep, but if the difference between the primary side and the secondary side is enough, then I could have 120,000 volts over here. So now what do I have? Kilovoltage. I've got kilovoltage. Now I can shoot a chest x-ray, okay? But I still got some things I got to overcome. Eventually what I want to do is I want to take all this energy and I want to send it across the x-ray tube. The x-ray tube's going to, I should have drawn this sideways, but x-ray tube is going to look, no, I just drew that exactly backwards. Looks something like this, okay? So eventually what I want to do is I want to run this through the x-ray tube so that when I'm ready, I can take and I can send the electrons across the tube really, really fast and create x-rays, okay? So I've got a secondary circuit. What have I dealt with here? The only thing I've told you about is primary and secondary, but which one of these components is it? Voltage. We still have to deal with amperage. So we have a secondary circuit that comes off of this, okay? And that is our filament circuit. We also have a rheostat in this one, and for whatever reason, they want to draw the rheostat in the filament circuit to look kind of like that. But it's essentially the same thing as this. We can turn up or turn down the amperage, right? So we turn up, turn down the amperage with this thing, but I'm still working off of maybe 120 volts. 120 volts. Okay? Anybody worked with electricity? Ever? Yeah, I have. You just didn't know it, you know.
Changing like an outlet out.
Yeah, change that. Okay, okay. What did you turn power off?
Yes.
Yeah, good. Okay, so you've dealt with electricity. Wintertime, what happens? What you got? Nothing. She don't want to say. She don't want to say. Okay, what happened? What happens in wintertime? You just walking along, you reach for a door handle or something like that. What happens? You get shocked. It's static electricity. It's moving electricity. So do you have to touch the door handle before the electricity jumps? The answer is no, you don't. And if it's in a dark enough room, you can actually see it, right? You get that little spark. Okay, so in the same way, electricity, you know, if we put components in a electric circuit thing close enough together, electricity will jump. So we don't want electricity to jump before we're ready for it to. So what we have to do is we have to have controls in place so that we don't apply this high voltage until we're ready with our amperage. So what we've got is this, and we're still looking at 120 volts, but 120 volts would make it jump across the X-ray tube, and we don't want that. So what kind of voltage do you think we might want on our filament circuit? High voltage, low voltage to keep it from jumping? We want low voltage. So our voltage down here might be 25 volts. Anywhere between 25 and 40 volts. Okay, so if this took low voltage and made high voltage, how could we take this and make it low voltage?
The opposite.
Exactly, doing just what the transformer here did. So we're going to have squiggly lines on this side, and in this case we're going to have a lot of squiggly lines, and in comparison on the other side we're going to have fewer. Exactly. So now we've taken our voltage from 120 volts down to maybe 25 volts, and we plug it into the X-ray tube, and this circuit here, this lower circuit, we call the filament circuit, is the first circuit you energize. All right, so whenever somebody took an X-ray yesterday, you might have noticed things happening. When they get ready to take an X-ray, they just push the button and it beep, and it went, no, what'd you hear? There you go, rotor. Okay, they even, you know, sounds like they even told you a few things yesterday. That's awesome. So you rotor up, okay, so you're gonna hear that. And what they mean by that is two things. So this thing right here, any kind of electrical device is gonna have two components to it, two odes. It's a diode. So you have a cathode and you have an anode. So the anode is this big flat thing here, and I'm going to show you that later in the semester too. So the anode, what the anode does is it rotates, and when they say rotor up, that's what they're talking about, is your machine won't shoot for 1 full second after you, even if you push the exposure button all by itself, it won't let you get an exposure for 1 second. It takes 1 second for this to spin up to the speed that it needs to be spun up to, okay? So it goes about 3,000 RPM. So it goes from a dead stop, 3,000 RPMs in a great big hurry. Okay, so in that time, two things are happening. That's getting up to speed, and we're going to use electromagnets, and I'll explain that later in the semester. We're going to use electromagnets to make that happen. And at the same time, we're energizing this circuit down here, and we're turning that into a light bulb. That's all it is at this point. It gets hot, just like a light bulb, incandescent light bulb. Your LEDs and things like that don't really get hot. But have you ever dealt with a light bulb that had a filament?
Mm-hmm.
You ever touched one after it had been on for a while?
Yes.
Yeah, it's like touching a toaster filament. It's hot, right? So it gets hot, it glows red. We have to have that, okay? So when they say rotor up, that's what's happening. What you're hearing is that thing starting to spin. Okay, 1 second later, you're ready to shoot. So it's spinning that and it's heating that up. Okay, now you're ready to go. But you're working off a low voltage at that point to keep the electrons from jumping across the tube until you're ready. So most of your X-ray tubes either have, or X-ray machines, the control panel they have two buttons, and really probably three. One is a prep button, and that's your rotor button, and the other is the exposure. Okay, you can make an X-ray just by pushing the exposure button, but again, it's not going to give you an exposure for 1 second to give all this time to go. Okay, so the exposure button is where we energize this portion here. Okay, so once we energize this portion here, we're going to also plug this into the X-ray tube like that on either end of the X-ray tube in order to complete the circuit. You ever heard of a short circuit? A short circuit basically means there's a break somewhere in that, okay? So we have to have electric flow all the way through So the high voltage circuit, you know, this circuit just goes through the filament. So you got attachments at both ends of that, so you don't have a short circuit. And then you've got, on the high voltage circuit, you've got plug-ins at both ends of the X-ray tube to complete the circuit. Okay? So once you push your exposure button, now you energize this portion so that all those electrons that collected to make your filament hot travel across the X-ray tube at really fast speeds. How fast? Really fast. Very good. Very good. Really fast. It's miniature lightning bolt. Is exactly what it is. It's miniature lightning bolt. What controls the speed is your voltage. The higher the voltage, the faster they go across the X-ray tube. So we're going to talk about energy, I think, in chapter 2. We're going to go through fundamental physics. We're going to talk about different types of energy. So once we have electrons positioned here, that's what we refer to as potential energy. They're not really doing any work, except not the kind of work we want, except they're heating the filament up, but the kind of work that we want to do is to create X-rays. Right? So they're not doing that yet. They're just heating this thing up, getting them ready. So we're going to say it's potential energy, and what controls the potential energy is, again, our KVP. KVP does a lot of stuff. We've got a lot of names for KVP. Potential energy, electric potential, penetration, you know, just a lot of stuff. So at this point, the electrons, once we press the exposure button, the electrons travel across the tube and they smack into this thing really, really hard. They're traveling really fast. So the speed, the upper register of the speed is maybe a third of the speed of light. They're really, really, really moving fast, okay? You don't see that. You can't see that for reasons we'll talk about later in the semester. Sometimes your patient, you know, you make an exposure and maybe there's something outside of the room that made a noise, and you should get an audible indication that you made X-ray exposure. Some sort of beep should take place, and you probably heard that yesterday. And if you don't hear that beep, then one of two things: either something loud happened and you couldn't hear it, or you just didn't get an exposure. One of the two. Your patient sometimes will say, "Well, I saw the flash. I know that, you know, it is shot." They can't see the flash. And we'll explain that later in the semester. It's impossible. Just nod your head and say, "Okay." All right. If you don't hear the beep, you know, give it a second. See if your image comes up. If it doesn't come up, well, you must have moved, so we got to take another one. Right? You'll learn all the proper lies to tell your patients why you need to repeat. So anyway, we feed it alternating current at the, which is a type of, so that we create a changing magnetic field so that we can adjust our voltage. So then we feed that into a high voltage transformer. The purpose for the high voltage transformer is to turn voltage into kilovoltage, right? So we adjust our kilovoltage there. We don't have kilovoltage yet, it's still just voltage, but you know, it's anticipation of becoming kilovoltage, so that we can send those across the tube at varying speeds so that we can create X-rays. Okay, everybody good with all that? All right. Also down here, we've got another rheostat here, which is really our MA selector. So what you're going to find out is what we have is milliamperage seconds, and we're going to refer to that as mass. Okay, so we have two components to mass. One is milliamperage, one is the time that you make your exposure. All goes together to create mass. More on that later in the semester. But anyway, what this circuit does, and is what it's responsible for, is heating the filament to get us to the proper temperature and to create enough electrons in this on and around the filament to give us enough electrons to travel across the tube, give us proper mass. Okay, what we call this thing here, the filament, and the electrons gathered around it would be thermionic. What does therm mean? Okay, what is an ion? Oh, very good. It's a charged particle is definition of ion, but in this case, and that's how you get to ionization is too many or too few electrons. So yeah, that's atomic structure chapter. But for now, it's an ion is just a charged particle. Well, the only charged particle that I've drawn up here is a electron, right? So it's an electron. So thermionic means hot.
Electrons.
Hot electrons, right? So this is thermionic emissions. Emissions of hot electrons on and around the filament, and we also call that an electron cloud. Okay, really pretty much means the same thing for our purposes. So the filament circuit does all that. The high voltage circuit sends them across the X-ray tube at very high rates of speed, so they'll smack into the target and create X-rays. We hope. All right. So everybody okay with this? Because I'm either going to have to move the tripod and go over there, or erase all this. What do you prefer? Okay, we'll erase it. I'll find an eraser. All right, so once they travel across the tube and hit the anode, the target, exactly. So on the anode is the entire assembly. All right, so on the anode we have an area that we refer to as the target. All right, so the target's not the entire anode, it's a portion of the anode. So if we're looking straight down onto the anode, what we've got is a great big thick chunk of tungsten. And I'll explain why we use tungsten later on. But if we're looking straight down onto the anode, the target area is just an area around the disk, okay? So the whole thing's not the target. The target's a very small portion of the anode itself. So the reason we rotate the anode is to kind of disperse heat. And the reason that's important is because upwards of 99% of what we create in the X-ray tube is not X-rays. It's heat. It's heat, right. So what happens if you get something too hot? It melts, right. It's going to melt. So we got the filament that's creating a lot of heat. We send these electrons across the tube that smack into that thing. Anytime you have friction going on, and electrons are going to create friction, what are you going to create? Heat. You're going to create heat. You create heat on the filament. You deposit the heat there. You create more heat as the electrons go back into the circuit. You got heat, heat, heat.
How
I'm
hot does it get?
Well, you can melt the anode, but the melting point of the anode is 37, as tungsten is like 3,700 degrees Celsius. So a lot.
That's a lot.
It's a lot, yeah. Yeah. So by melt, you know, you're going to etch it some. You're not going to just completely melt it, but it's enough that it will put some damage on it. Okay, so we got to do things to mitigate that heat, to get rid of some of that heat. And one of the things is to rotate that. So if we took that laser beam like lightning bolt and we put it all in one place, what's going to happen at that one place?
All going to centralize.
It's all going to centralize and you're going to melt your anode. Yeah, you're going to screw up your target. But if, is all the heat going to stay right there?
No.
No, it's going to spread out. Now, if I take that and I turn it around real fast and I move that target area, then it's going to spread out more efficiently. Okay, that's the purpose for rotating the anode, is to spread out the heat. Okay, so once they hit that, there's one of two ways that we're going to create X-rays. All right, so what are you made up of? Matter. Matter is made up of atoms, right? So this is made up of atoms as well, right? It's just all tungsten atoms. Now, the reason we use tungsten, we'll talk about later in the semester, but fundamentally, it's because it's a big fat atom, okay? So big fat atoms are better at creating X-rays than non-big fat atoms, all right? So what I mean by that is we've got a great big nucleus and we've got a lot of electrons. You know, our atomic structure, as we understand it, is that you've got a well-defined nucleus full of what subatomic particles? Protons and neutrons. And then around that are shells of electrons just spinning all around, going through the nucleus, going around the nucleus and whatnot, right? So you got a lot of different shells in the tungsten atom. The atomic number is 74, which means we have 74 protons. And in a neutral atom, you'll have the same number of negative charges, or electrons, as what you have positive charges, so we have a lot of electrons. We have a big nucleus and a lot of electrons, okay? So what we're going to do is we're going to send these electrons. I will bring some, nobody's any better than another. We're going to send these electrons as into the target, but it's kind of a shotgun approach. You're just lining up these electrons, you're throwing them at the target, and you're hoping to get close to the nucleus of the atom. Now think of the atomic structure as kind of being like a solar system for just a minute, okay? Most of y'all are probably too young to remember, what was it, Shoemaker-Levy that came through the solar system as a comet that came through the solar system. You remember hearing about that anywhere? Oh yeah, I forgot about them. yeah, there was a cult that thought that there was a spaceship in the tail of that was going to suck them up and, you know, take them to paradise, whatever. It did not happen. They found them all dead, every one of them. What's that?
We don't know really.
Well, yeah, I guess you're right. It could have happened. Who knows? Maybe we all missed the cut. But at any rate, we got what kind of charges in the electrons?
Negative.
Negative. We got positive charges in the protons. So positive and negatives, they do what? They attract. Yeah, that's how you mouth it. Speak up, spit it out. They attract, right. So now the reason I brought up that comet is because Jupiter is kind of the vacuum cleaner of the solar system. Biggest planet. If something comes through the solar system, there's a chance that, you know, that Jupiter could pull it in to its orbit or potentially into the planet itself. Shoemaker-Levy, you can look it up. It's really spectacular. You can look it up on YouTube and you can see the impact places where the comet broke up as it entered the atmospheres as it got close to the planet. It broke apart and impacted on the planet. So Jupiter, Shoemaker-Levy, all right? So if it gets close enough to the nucleus of the atom, then the gravitational pull of the nucleus of the atom will distort the path of that electron, okay? So let's say we were using 120 kVp as an example earlier, 120 kVp worth of energy in this electron. That's how fast the electron is moving, and we're going to refer to this as an incident electron. When I draw electron travel, they're going to be in relatively straight lines, okay? So that's an electron travel, okay? Amy, I think she's already kind of dropped hints at frequency and wavelength, right? Okay, if I draw a squiggly line in the path of something, that's an X-ray photon, okay? Frequency and wavelength. If it's a straight line, electron. So this is what we refer to as an incident electron. So if it gets close enough to the nucleus of the atom, then what will happen is it will lose some of that energy. It'll lose some of that energy. It'll also cause it to change directions and go off in a different direction, okay? So you're driving along and you kind of whip the wheel of your car, and providing you don't roll over, are you going to keep traveling at the same speed? No. What's going to happen? You're going to lose some speed, okay? So the same thing happens here. The electron loses some energy. So it comes in with 120 kVp, and let's say it gets close enough to the nucleus of the atom that it exits with 60 kVp worth of energy. What's that? You cut it in half, right. Where'd that energy go?
Heat.
You're going to create a lot of heat, but in this case, it's going to do something different. Some magic. Okay, so according to quantum physics, energy is not going to be created or deleted. You're just going to transfer it from one type to another, or from matter to energy to matter again. Okay? So if this 120 kVp electron enters and it leaves with 60 kVp, that 60 kVp has to go somewhere. And it's going to go somewhere in the form of a X-ray photon, right? So the energy level of this X-ray photon is going to be equivalent to the difference between the incoming energy and the outgoing energy, which means that X-ray photon is going to be 60 kVp. Right. So if it lost 100%, if it came in with 120 kVp and it left with effectively 0.1 kVp worth of energy, then what is the energy of that X-ray photon? We're very close to 120 kVp, right? So these can occur at any level, and these are they're caused by the slowing down of the incident electron. So you mash on the pedal that's going that way in your car, and what do we call that pedal? It's brake pedal. It's brake pedal, right? So the guy who discovered X-rays, he didn't invent them. Somebody else invented the machine that he discovered the X-rays with. His name was William Röntgen. So he's a German guy. So a German guy names this, and he names it braking X-ray, but he names it braking in German. So that word, I'm not going to write it out because my pen's dying, but it's called Bremsstrahlung. Okay, so big, fat, long word, Bremsstrahlung. We're going to shorten it to Brems. Brems X-ray creation involves the losing of energy of the incident electron as it gets close to the nucleus of the atom, and the energy of the Brems is going to be the difference between the incoming and outgoing X-ray photon. So again, this is like chapter 7. Don't stress about this. This is just what we're doing this semester, okay? The other way is that if the incident electron hits an orbital electron and knocks it out of place, then we can also create an X-ray photon based off of that, okay? That's a little bit different of an interaction, and that's what we refer to as characteristic X-ray creation. All right, so the characteristic X-ray creation kind of follows the Brems model in that these electrons are held into place by a specific energy level. Okay, so it's held into place with 69.5 keV. Most of the time they'll just knock the 0.5 off and just say 69 keV, kilo electron volts. So it's held into place, and kilo electron volts for our purposes in kVp are they're equal. Okay, so they're equal. They're a different perspective, but they're equal. So if this energy is higher than this energy, would this electron knock that electron out of place? Yeah. Okay, so it knocks it out of place. It goes off in a different direction. It's still an electron. It might drop out of place and pop right back into place. It doesn't really matter. But if this 120 kVp electron knocks that one out, then we're going to create an X-ray photon that's equivalent again to the difference. Mathematically, that's subtraction between this and this. So what would that be? Now you got to do math, right? About 51. Yeah. So about a 51 kVp X-ray photon. kVp X-ray photon. Okay? So the reason we call this one characteristic is because if you change the target material, we're using tungsten. If you change it to gold, it would be higher. If you changed it to lead or aluminum, it would be lower. Okay, it's characteristic of the X-ray. This binding energy here is characteristic of the tungsten atom. In mammography, we use a different material for our target. We use molybdenum. Okay, so the characteristic X-rays created off of molybdenum target are totally different than diagnostic. Okay, for again reasons we don't need to know right now. So those are the two ways we create x-rays. And the statistics say, you know, the only one of the characteristics that we're interested in are the innermost shell. So we do create characteristic off of any shell. We'll talk about that later in the semester, but the only one that we really focus on is the innermost shell. So what they say is that 85% of our x-ray beam comes from right here, Brems, with 15% being the remaining characteristic. And, you know, okay, so just real quickly, I interject a lot of opinion. I can't really wrap my mind around even 15% being this, okay? Statistically, you need to know this for testing, but if you're like this tiny thing hitting that tiny thing, which are just a few of those things orbiting around this great big thing, the math doesn't math to me, right? So if you struggle with it, that's fine. I do too. But this is what you need to know for the test is 1585. Okay. So most of your X-ray beam is created in the Brems spectrum, which could occur at any level. 15% are going to be your characteristic, which are going to be at very discrete levels. Okay. Everybody good with this? Okay. So now's where it gets confusing. Now's where it gets confusing. So how does this translate to what goes into the patient? And what happens in the patient? Well, pretty much the exact same thing happens inside of the patient. Okay? So I'm going to leave my atom up there. I'm going to erase this. And I'm going to erase my lines. And I'm going to say that this is, I don't know, a water molecule inside of the patient. So it's oxygen. And get rid of those. So if a photon, because it's a squiggly line, hits an electron inside of the patient, and this photon is carrying, let's go with the lower energy, 59 kVp worth of energy with it, and it knocks that electron out. Knocks that electron out. First off, what do you have? What happens when you
Ionization.
add or remove an electron?
Ionization.
Ionization. You got ionization inside of the patient's body. You got a free radical, essentially, is what you have. What happens if that's on a DNA strand? You got a break, a potential mutation. Okay? All right, so if it ejects that, now you've got, again, an ion, and it's going to try to replace that. That might jump back, right back into place where it was before, and probably everything's going to be okay. But that X-ray photon now loses energy. It scatters off in a different direction, and it loses energy, but doesn't. Conservation of energy says
It's transferred.
it's transferred. It's transferred. It's transferred. Right. So it's transferred. You know, you've got the energy absorption there. Our X-ray photon now has a lower energy level, and it's scattered off into a different direction. So there's a number of different things that can happen inside of the patient. This is one, and it's what you'll hear in Amy's class as Compton interaction. As scattered X-ray photons. Scattered bad. Okay? It just messes up the image. It's not any worse for the patient than other types, and it's even better than some other types for the patient. But for the image, it's bad. It's Compton scatter, it's bad X-ray. We want to get rid of those. We're going to teach you how we're going to get rid of those. Especially next semester. Amy's going to hit it this semester, and we're going to hammer it home next semester. Okay, so some X-ray photons will go through the patient and not touch anything at all. And that is the best X-ray photon for the patient. And that's a good photon for us as well. This gives us our dark areas on the image. So you shoot a chest x-ray. Anybody see a chest x-ray yesterday? Okay, good. So the dark areas on the x-ray, on the image, are because you've got a lot of these that transmitted straight through the patient. You probably have some of those too, but you got a lot of these that just transmitted through the patient. The third is if, let's say, the binding energy inside of the patient, or let's say more than that, let's say this photon here dropped to, I don't know, 20 kVp worth of energy. It hits another atom, electron, and it absorbs all of the energy. It imparts all of the energy to the patient. Now the patient is, again, ionized, and yet at the same time, they've absorbed that entire X-ray photon. Okay, so it's transmitted inside of the patient. Worst scenario for the patient, or the worst type of photon, is a total absorption. So you hit a bone, okay? So you hit a bone. How do bones show up on X-rays? Very light. So a light area on the X-ray indicates that you've got a lot of absorption, okay? Dark areas, a lot of penetration, some scatter radiation. Light areas, some scatter radiation, and a lot of absorption, okay? So, what's the wrap up to this? Some little kid is gonna ask you at some point, how are X-rays made? And what's your answer gonna be? Well, yeah. Do you have, yeah, you're gonna say, do you have 52 minutes? Yeah. You give them a rundown. We use electricity, adjust electricity to, create an X-ray beam. X-ray beam goes inside of your body. Some absorbs, some transmits. That's it. So, how you feeling?
Excited.
Yeah.
And
You kind of loaded up? Okay, again, this is all semester long. We're going to take all this stuff and we're going to break it into manageable pieces and we're going to just eat the elephant.